So now we have our second problem, which concerns now the comparison of the true period of a pendulum in comparison with the approximation period um, reg- uh, in accordance to answers from number 29 and from number 30. So based on our previous results, we have just accounted this part of the pendulum, which is one swing only, and just let's say half of it. So one period is equal to one full swing back and forth, but then we have only accounted this one. So therefore, um, in accordance to answers number 29 and 30, in order to get the period of such, we have to multiply it by 4 because the period from 29 to 30 is just a fourth of the real period of the pendulum that we are concerned about. So now, based from the answer from number 29, which is just this frequency, we could recall from our physics that our frequency is just equal to the angular momentum 2 pi f, and then which is consequently equal to 2 pi over t. Hence, our answer from number 9 is 2 pi square root of L over G. And accounting for the consequences that I have stated earlier, this will be times 4. Then based on our answer from number 30, this one, so we'll just have to multiply this by 4 because of, I repeat, the consequences that I have said earlier. Then now, recalling from number 30, the relation of k squared to sine alpha over 2, we have to solve for the value of k so as we could input it into the answer in number 30. So substituting the value of alpha, sine squared, this is sine squared, 90 over 2. So we have sine squared 45. Eventually, our k squared is equal to sine 45, which is equal to square root of 2 over 2, or just 0.707. So in order for us to get this value of k, just k rather, in order for us to get the value of k, we have to use a certain type of calculator or a certain type of table that we could only find in books or um, most easily on the computer. So we have here um, an elliptic integral of the first kind, an incomplete one calculator, where we can solve for the value of k. So we'll just have to input the value of k, and then we would click execute. And at this case, we have RK of 0.707, and then clicking the execute would give us RK of 1.855407468. So let me clarify this. This k of k is the value of this part of the answer from number 30. So therefore, our number 30 period is just 4 times this one, k of k, times our square root of L over G. So now, we will gonna realize what is the true period and the approximate period from the answers from number 29 and 30. Recall that our now number 29 question only approximated our theta to be sine theta, while our question from number 30 actually solved sine theta as sine theta itself. Therefore, our approximate period is equal to 2 pi times 4 square root of L over G, while our true period is equal to that one, L over G, the integral of 0 to theta, d theta, over square root of 1 minus k squared sine phi, and this is times 4. But eventually, this is just 4 times k of k because of the simplified calculations given to us by our technological help. So now, solving further, since we have to compare both, we will then have a ratio of our true period divided by our approximate period. Hence, we're gonna divide 4 times 1.85 407 468 square root of L over G with the approximate period, which is just then equal to 2 pi, or just 6.28 319 square root of L over G. Hence, canceling both sides, we'll get 7.41630 divided by 6.28319. Eventually, this is just equal to 1.18. Hence, our true period is 1.18 times greater than the approximate period.